All right, let's talk about one of the most important, yet kind of invisible, pieces of tech that makes our entire digital world work, the IP address. Seriously, it's the unsung hero of the internet, and today we're going to pull back the curtain and see why.
I mean, have you ever really stopped to think about it? You type a website into your browser, you fire off an email, you start streaming a show. How does your computer know where to even send that request? And maybe more importantly, how does all that data know how to find its way back to you and not your neighbor? That's the puzzle we're going to solve.
Okay, so let's just jump right in at the very beginning. What in the world is an IP address? Well, the easiest way to think about it is like a massive global postal service, but for data. It's the system that makes sure every little bit of information gets exactly where it needs to go.
So officially, IP stands for Internet Protocol Address, and it's basically the unique digital identity for every single device that's connected to a network. The postal address for a house is honestly the perfect analogy. Without it, your packages, or in this case your data packets, would be lost in the mail.
So if you remember one thing, it's this. An IP address equals a device's identity online. It's that one-of-a-kind signature that shouts, "Hey, I'm over here, this is me, send the cat videos to this spot." It's simple, but it's unbelievably powerful.
And what does it actually do? Well, it kind of has three main jobs. First up is identification. It tells all the other devices on the network who's who. Next is location addressing. It provides the actual path to find that device. And finally, communication. It's the bedrock that lets data flow back and forth. No IP, no communication. Simple as that.
Now, here's where the story gets really interesting, because not all IP addresses are the same. It's kind of like a little drama from internet history, the story of the original system called IPv4 and how it ran into a huge, huge problem, and how its successor IPv6 came to the rescue. And this number right here, this is what caused the whole crisis, 4.3 billion. That's how many unique addresses the original IPv4 system could create. Back in the 70s, that seemed like a practically infinite number. But then came the explosion of smartphones, laptops, smartwatches, smart everything. And pretty soon, we were basically out of addresses.
And this is the solution. See, IPv4 was a 32-bit system that gave us our 4.3 billion addresses. IPv6, the new kid on the block, is a 128-bit system. Now, the jump from 32 to 128 bits might not sound like much, but the difference in the number of addresses is, well, it's astronomical. We went from billions to undecillions. That's a 34 with 37 zeros after it. It's a number so big it almost doesn't make sense. Just to try and wrap our heads around that, with IPv6, there are enough unique addresses for every single grain of sand on our entire planet to get its own IP address. And you'd still have trillions and trillions left over. So yeah, the problem of running out of addresses, it's solved. Forever.
But you know, before IPv6 was everywhere, engineers had to get creative to make the limited IPv4 addresses last longer. And their clever solution created two different worlds of IP addresses, public and private. Let's dig into how they work and the critical piece of tech that connects them. Okay, so a public IP is like your home's mailing address. It's totally unique in the whole world, and anyone can send mail, or data, to it. A private IP, on the other hand, is more like an internal employee ID number at a big company. It only has to be unique inside your office, or in this case, inside your local home network. The outside internet can't even see it. So, how do all your devices at home, your phone, your laptop, your game console, all with their own private IPs, get on the internet? The magic here is something called NAT, which stands for Network Address Translation. It's a clever feature built into your router that acts like a receptionist, letting all your internal devices share that one single public IP address. Now, it was a brilliant hack that kept the internet from breaking for decades, but it did add a layer of complexity. It made some things harder, but it saved the day for IPv4.
Here's the play-by-play. Your laptop, with its private IP, wants to visit a website. It sends the request to your router. The router then cleverly swaps out your laptop's private IP for its own public one and sends the request out. When the website sends a response, it comes back to the router's public IP. The router then checks its little internal logbook, its NAT table, sees that the original request came from your laptop, and forwards the data right along. It's doing this constantly, millions of times a day, without you ever noticing.
Okay, so we've nailed down the fundamentals. Now for the really important part. Let's connect all this to how modern software and applications are actually built. Because when you're designing a system, understanding how public and private IPs work together isn't just nerdy trivia. It's the absolute foundation for everything, from security to making sure an app can handle millions of users. And this right here is a perfect example. You, the user, connect to a public IP address. That's the front door to the application. This is usually a component called a load balancer, which is like a traffic cop. That load balancer then sends your request inside the private network to a backend server with a private IP. Then, that server might need to grab data from a database, which also has a private IP. See what's happening? Only the front door is exposed to the internet. Everything else, all the important stuff, is tucked away safely inside. And the impact this has on designing systems is just massive. Think about scalability. Need to handle more users? Easy. Just add more servers with new private IPs behind that load balancer. Security is fundamentally built on this idea of hiding your critical components on a private network. Things like load balancing, routing, and making sure your app doesn't go down, what we call high availability, it all hinges on this intelligent flow of traffic between public and private IPs. It's the blueprint. Let's just double-click on security for a second because it's so critical. The IP address is your first line of defense, truly. You can use IP whitelisting, which means only certain trusted IPs are allowed in. Or you can do the opposite, blacklisting, to block known bad guys. Firewalls and security groups in the cloud, they're basically bouncers at the door, checking IPs to decide who gets in. And separating your networks, like keeping your testing environment completely separate from your live production environment, that's all done with IP routing. It's the core of network security.
So let's bring it all home. After all this, why does this seemingly simple string of numbers matter so much?
It really boils down to these core system functions. Communication, IPs are what connect you to a service. Scalability, they let you add new servers on the fly. Load balancing, they're the targets your traffic cop directs requests to. Security, they create that vital wall between the public internet and your private network. And fault tolerance, they let you reroute traffic if something breaks. So just remember this, when you're talking about system design, IP addresses are so much more than just numbers. They are the absolute foundation. They're the bedrock of how modern systems connect, talk to each other, and scale up to serve millions of people.
And that brings us to a final big thought. With IPv6 giving us a practically bottomless well of addresses, we're marching into an era where literally everything can be connected to the internet. Your car, your toaster, tiny sensors in a farmer's field. So it really makes you wonder, as this idea of a unique digital address expands way beyond our computers, what does the future of digital identity really look like? Something to think about. Thanks for joining me.